wait until they touch each other. What if you have like a 2-micron gap between them? Perfect, but we cannot make every single gears in the machine like that. So they usually put some relaxed tolerance. So that's why every gear motor you have, servo motors and LDO motors, you'll feel this, oh, why is it jolting? That's because the backlash accumulated through multiple stages. Of course, you can design one really amazing gear, perfectly matched, so these gear teeth are almost matching like this. And then, oh, there's no backlash, but it's really hard to be perfect. If you're a little off by jamming in, you're going to have huge friction. Because these gears are really made to be very last and long, so these are really hard. So if you jam a little bit harder, like if your distance is like a couple micron off from that distance, and then you're going to have really high stress, and then you're going to lose a lot of energy. So most gears are, in order to be tolerant, so they have a pretty relaxed backlash. If you get far apart, that gets worse, and also stress on the gear teeth gets worse because their point of the contact gets far away from the center, average, so gear teeth can break easily. So still need to precision machining, but still the constant loss doesn't change. So distance off doesn't mean your machines are wobbling or chattering. Some people ask about why gear ratio. We have a 200 to 1. This is I don't remember what gear ratio is, like more than 200 to 1 gear reduction. Why do we need this many stages? Like some people ask that why. Like if you think about the gear ratio from the motor to the first gear is about 7 to 7.2, and this 10 to 48 is about 4.8, and 10 to 46 is about 33.6, and 16 to 42 is 1.3. It's like 1.3 to 1.7. A lot of planetary gears and many gears that they're roughly around 1.3. The reason is if you want to make 201 gear reduction, if you grab pinion gear of the motor about this big, and then the other gear should be 200 times bigger. So it doesn't really fit into a nice package. So this is the most compact way to create a large gear ratio using a compound spur gear set, except harmonic drive. I showed you last week. So one more thing I want to show you, I'm going to introduce later, is planetary gear. Remember, I hammered the output of the servo motor and the gear brake, because if you think about any high torque from this output, and what's the next thing that have a lot of stress is the one gear teeth, one or two. It depends on the phase. That little tiny gear teeth take all the forces. So spur gear is compact and nice. You can make it very small, but become really fragile because you're relying on one gear teeth. Imagine you're rotating really hard, like an impact force, and then that gear teeth is going to break, right? So that's why the planetary gear is designed. You can distribute forces among 4 gear in this case. 3 are much more common. In this case, I really wanted to distribute more, so I have a 4. Imagine there's a pressure separation force between this gear and this sum gear. I didn't show here. The sum gear is this. The reason why this is called the planetary gear, this is the sun. These are planets. And they are spinning like a planet. And the sun is always spinning faster in this case. So that's why I call it planetary gear. This is a really good design because you can distribute forces into 4 points. And then separation forces are all canceled out. Right? Separation force between sun and this one will be along the vertical string, where all 4 forces are canceled out. So there's no net force in this case. This shaft, they're separating or locked, and then your structure should be able to handle it. In this case, they are all even out, and this one piece can handle this. So it's a really good design. I'm going to show you how to calculate the gear ratio on this one. I'll show you the other side of this one. You can see like this. And then ring gears is outside. We didn't show you the ball screw last time. So this is a ball screw. One of the good way to, it's very common in factory to convert rotational motion to the linear motion. So usually they mount something here and they spin the shaft really quickly. I have to show because it's moving very slowly. Typically, when you rotate once, there's a little, you can see the thread, one pitch is moving. So this is about 1.5 millimeters, 2 millimeters. So when this guy rotates once, it moves 2 millimeters. So you can, that's how you can calculate the velocity ratio or the force calculation. It's hard to, you cannot really see it. You can find the video in the YouTube. There are actually very small, tiny holes. The tiny ball bearings are wrapped inside this package. So, and interestingly, the balls are following this thread, and then once you reach the end, it climb out and then join in the other side. It's pretty cool. You don't have it because this is $250 per piece. I'm sorry, I'd like to give you this. It's very nice. There's ball bearings are reducing friction a lot. You have an alternative, which is really cheap. Threaded nut. It's not the ideal because this threaded rod and the nuts are designed to lock things, not transmit power. So friction is not great, but when these two are both rigid, like the steel, that's actually okay. So I recommend to use a nut to transmit linear motion to the rotation motion to linear motion. Some people use a plastic piece and then thread it inside using PAP and then put it in. It feels smooth, but when you apply forces, the friction goes up pretty high. So I recommend to use rather nut than plastic piece. There's actually things called the Acme rod, which is actually designed to do the same thing without having ball bearings on. I want to show you the most complex version of this, and this is the most impact robust mechanism in linear rotation to linear transmission. It's called the planetary roller screw, and again, it's extremely expensive. You might figure out why that is by looking at this video. There are a lot of threaded rod, and both sides of the threaded rod has actually gear teeth on it. So when it's assembled, those many 8 threaded rods are rotating like a planetary gears. But what sun gear is not a gear, sun is actually a thread. It's really strange. If I give you a question to calculate the gear ratio on this one, it's going to be pretty complex. So those threaded rod is not moving with respect to the cage, they're just spinning because those are actually geared. The outside is geared, right? So they're rotating like the planetary gear, but in the middle one, they're conjugating like threaded rods, and then it goes in and out. Why this is designed this way? Because imagine there's really high impact coming from the shaft, and the contact surfaces are like first of all, there are many of them, and contact surfaces are not a point contact. Ball and screw, there's a lot of balls in the surface, but ball to the surface contact is always point contact. So the ball can crack or get damaged, and then you use a lot of power, friction goes up. Here, actually, the line contact, everything's on line contact. So anybody know the roller bearing instead of ball bearing? The ball bearings are literally, steel balls are in contact, conjugate, so you can minimize the friction. Roller bearings are actually rolled. There's a cylinder is running around the shaft, so you can actually have a line contact. It's much stronger. This is kind of roller bearing version of ball screw. It's very rare, but it's, I saw people start using the robotics when they need a lot of impact. Unless you use the hydraulics. Hydraulics are good in impact, but there's other issues. All right, so we have a lot to cover, so let's go on. Today we're gonna talk about degree of freedom, which is pretty easy. It's not intuitive, but it's a pretty easy process. You just need to remember one thing very easily. And I'm gonna go into the virtual world, which can be very confusing. So I want you to be really focused on this, and And I will explain why we're teaching this even though it's so confusing, because in other sense, humans are actually a lot better at geometry than forces. You can't imagine how things are moving visually, but we're not really good at imagining what force that could be there. Like, forces are invisible, right? So virtual work is some sort of a dual to a 3-by diagram. 3-by diagram solving the problem using only forces, and then virtual work is solving everything based on geometry and the movement to infer what the forces will be. In order to do that, I need to introduce the concept of instantaneous center rotation. So those will be a little bit confusing, but I hope that it's going to be really useful for your design. So let's define a few terms. Generalized coordinate is defined by a set of independent configuration parameters. So I can give you an example. In your machines, most of them are going to be one degree of freedom system, which typically means you have only one parameter to define the state of configuration, the static state of your machine. So I can give you an example. It's really simple, really easy to answer. It's written in the slide. How many parameters you need to, how many numbers you need to give somebody so that he can configure it in a way that you want it. In this design, there's one link. One is anchored around the pin joint. There's another pin joint between two links, and then you can move around, right? I want to give somebody a minimum set of numbers so that he can configure this mechanism. How many numbers do we need? We need 2, right? As I said, the Q1 and Q2, right? If I know this angle and then this no angle, I can't exactly know what is configuration, the shape of static state of the machine. So that, how many, those are called the generalized coordinate, and then how many of them are called the degree of freedom. So how many degree of freedom in this case? 2 degree of freedom system, okay? I can give you another example. How about my shoulder? How about my shoulder? How many degree of freedom? How many angles or how many numbers should I give you, say, to copy my shoulder? Imagine this is one rigid body. So let's say you can define it from way. If you look at from the top, 1 degree of freedom, which tells you coordinate, or vertical coordinate. And there's another one is like this. What else? If I tilt, like lock my elbow, I can still rotate this thing, right? So I'm not rotating my wrist. I'm rotating actually entire arm. So I need a 3 values to define this configuration. And I'll tell you what kind of joint it's called. This is called the ball and socket joint. Yeah, so I wanted you to remember this is pretty basics. It's nothing complex. You need to remember these words so that whenever you're confused about it, you need to repeat the words. Oh yeah, that's actually what we're doing. So, are you comfortable with those terms? How many numbers to define a configuration is the degree of freedom, and those coordinates are called generalized coordinate. So, in 2D, things are fairly simple and cool, easy. The procedures like to count the number of rigid bodies, and then every rigid body has how many degree of freedom? 3 degree of freedom. Why? Because in object in 2D, this is a world in 2D, raising the board, and I need to how many numbers I need to define to exactly define describe the configuration of this guy. I need to tell how high is this. I need to tell how wide, where it is in the lateral position, and then I need to tell what angle it is, right? So each rigid body has a 3 degree of freedom. And whenever you start creating a joint, you're getting rid of the degree of freedom. You're constraining them. You're kind of putting in the jail, basically, right? So it depends what kind of joint. In 2D, it's pretty simple. And most regular joint, if I nail it, I brought a nail and hammer it down here. Now, how many numbers I need to say, define to really define the configuration of this guy? How many numbers do we need? Just 1. If I say an angle, and I know exactly how it looks like. what if I put this on this rail and I can't rotate anymore? And this is called a sliding joint, right? You can create sliding joint in your machine to lift things up, right? And then you kill the rotation basically. And then, and because of sliding constraint, you cannot move up and down. So you need only one number to define exactly where it is. So typical joint in 2D, get rid of 2 degree of freedom from 3 degree of freedom. So I can give you an example. So typical example is 4-bar linkage. We're going to do this multiple times today. This is anchored on the ground, and there's a 1-pin joint, 1-pin joint. And how would you calculate the degree of freedom in this guy? First step, count the number of rigid bodies. How many do you have except the bottom, except the grounded one? How many? 3, right? 3 rigid bodies. And how many degree of freedom of each rigid body when there's no joint? 3, right? So total, my brain is playing with me. Total 9 DL to begin with, right? Now we anchor the relationship. I start like, you have to play with this guy, you have to play with this guy here. I constrain them, and then each joint get rid of how many degree of freedom here? 2. So how many joints do we have? 1, 2, 3, 4. So 4 joints, and each joint get rid of 2 degree of freedom. So we have 8 constraints. So how many degree of freedom left? 1. That's why we have only 1 degree of freedom. If you tell one angle, you will exactly define how the configuration of the system. It's pretty simple, okay? So let's do another example. It could be a little confusing, but there's one joint and another joint. Sorry, we've been missing this. Oh. This is for the recording of the lecture. I hope this is not necessary because everybody's here. This is a base. Imagine this body is not moving. There's a one joint. This is a floating part, so you can think about 1 joint, 2 joint, 1 linkage, 2 linkage, 3 linkage, and 1, 2, 3, 4. How many rigid bodies except the one that I anchor on the ground? How many moving rigid bodies? Same as a 4-bar linkage, right? So 1, 2, 3. And how many joints? 4, right? So 3 times 3 is 9 degree of freedom, and then we get rid of 8 degree of freedom, so you have 1 left. So how about once I add a servo motor? So this is a rigid, anchored on the ground. This is fixed. This can rotate about this joint. This can rotate about this joint and this joint. And then rest of the system is the same as before. How many rigid bodies do you see in this picture? 1, 2, 3, 4, 5. And how many degree of freedom of 5 rigid body? 15. And how many joints do you have? 1, 2, 3, 4, 5, 6, 7. So how many degree of freedom we lost by adding joints? 14. How many degree of freedom is this? It's 1 degree of freedom. Of course it's 1 degree of freedom. Otherwise, you need 2 motors, right? You need in order to control 2 degree of freedom system, you need 2 motors. There's exceptions always, and then you'll find these kind of exception machine in the real life, because if you make it perfectly parallel and copied, this thing happens. So these 2 joints are anchored on the ground. So how many rigid bodies do we have? 1, 2, stop moving, 3, 4, 5. We have 5 bodies. So we start with the 15 degree of freedom. And how many joints? 1, 2, 3, 4, 5, 6, 7, 8. So we need to get rid of 16 degree of freedom. This is a -1 degree of freedom. It's still moving. So when things are perfectly parallel,
it become like this. I actually designed something like this last semester. If you get rid of this part, it will still move exactly the same way. And if you remove like a whole bottom like this, then you're gonna have a problem here. But anyway, even though you remove this part, you're gonna have exactly same motion. This is a redundant system to increase stiffness so that you can resist more forces. So this is exceptional. When everything's are in parallel, you can create a system that moves even though it's the negative, degree of freedom is negative. This is one of the example. Linkages like this, and then there's another linkages like this. Typically adding one linkage like this, and then rotating this is enough to rotate this one. If this is anchored on the ground, it's anchored on the ground. But I want to be stronger. When I pull this guy handle pulling force really well, but when I push, this might crumble, it might buckle. So I want to add another joint at the bottom. As long as these are perfectly parallel, the lengths are same exactly, it will still move. But if you calculate degree of freedom, 1, 2, 3, 4, 4 times 3 minus how many joints we have? 1, 2, 3, 4, 5, 6. It says you can move, but it's actually moving because it's all perfectly parallel. So these are exceptions. So whenever you see any 2D machine, you should be able to calculate degree of freedom. Most likely the answer is 1, like this. How many degree of freedom do you think this is? All these pictures you see here are all 1 degree of freedom system. Surprisingly, this is 3D, I guess, now. Chuck Hoberman is actually working at Harvard, so you can actually meet him. He made a most famous toy based on this, and then he started making things for, this is pretty cool, expandable dome. Yeah, that's the toy you probably saw maybe when you were young. That's the toy. Hoberman Spear is a toy you play with a lot. It's a 1 degree freedom system. There are gazillions of links. I don't even know how many links do we have. Yeah, they made a pretty amazing stage. Yeah, this is the stage. Concert stage is actually collapsing like a iris of your eyes. This is pretty cool, isn't it? So I expect you to build something like that. And another kind of famous guy who utilized this 1 degree freedom system, Theo Jensen, wind-driven machine. This is still 1 degree freedom. I want you to go there and calculate, okay, how many rigid bodies and how many joints. Look at that. The problem with these kind of machine is because it's 1 degree freedom, the feeds is not going to work when ground is not flat. And there's not even a motor here, it's all wind driven. Biologies are relatively a lot more complex, but I want to show you one really cool video. I found it fascinating. So, Smarter Every Day. I don't watch all of them, but I watch a couple of them, and this is one of a few things I found fascinating. So when I was young, fish have a big mouth. It's always like go above and then like surround the prey and then eat. That's how we eat, right? That's what we think we eat. That's how we eat actually, right? But the situation in the water is very different. You need to create this suction literally. So opening mouth is creating a volume to create a suction negative pressure to bring the water in. That's how they engulf the prey, not necessarily going around them. So that suction is so powerful, you can actually get the air going through their gills. And in nature, as you see a lot, there are bizarre things going on. Look at that. What is that? See how much it come out? But how do they do that though? How do you think the fish can throw these things out and then create negative pressure at the same time? And there's actually a linkage system. Probably more than 1 degree freedom, but majority motion is still 1 degree freedom. This is, I film at the Science Museum. Real thing is a lot more complex. This is a simplified version. There's actually joints are created in a way that when you open up, it creates that kind of weird expanding motion that creates negative pressure and then engulf the animal, the prey inside the mouth. Let's move on to 3D. It's nothing different except that number of how many degree freedom do I have in the space if I have one rigid body? 6, 3 positions and 3 rotation. And then as soon as I create a joint, if I create a pin joint in the ground, for example, how many degree freedom do I lose? Now how many degree freedom I have if I have a pin joint? How many degree freedom, again, going back to the original word, how many numbers do I need to tell them to define this? If this is pin joint, how many degree freedom? This is 1, right? Used to be 6 degree freedom, now you have a 1 degree freedom. Because pin joint only allow you to rotate in a 1-dimensional space. So each pin joint get rid of 5 degree freedom from system. Okay, right? So the same arithmetic, except that there are many different joints in the 3D world. So this is revolutionary. It says 1 degree freedom system, which means you're getting rid of 5 degree freedom every time you add it on. Prismatic joint is the same, it's sliding joint. You're only allowed to have 1-dimensional movement, which means you're getting rid of 5 degree freedom. Universal joint, what's the best place you can see this one? Actually, some truck has this one pair. It's called the Cadon joint. A pair of the universal joint create a CV joint, constant velocity joint, and that's 2 degree freedom, different from shoulder because it doesn't have a rotation, right? And ball and socket is truly like your shoulder and your what is this called? Hip joint. Anyway, that's the hip joint and ball and socket. You can actually have a 3 degree freedom, right? So, which means it allows 3 degree freedom, which means you're getting rid of 3 degree freedom every time you're adding on. Okay? So, I will introduce something like a flight simulator. So it's quite complex. Something like this. Somebody just made it. I love this. So he just he bought 6 motors and connect this. It doesn't have same prismatic joint, but it just create a rotational motion. So it can create lateral motions and tilting and so on. So now I want you to bring out a piece of paper. At least as big as a half a letter page, and calculate how many degree freedom this guy has. And don't forget to put your name on top and your ID number, your student ID number and your name on top. And then calculate how many degree freedom this system has. There are 6 joints on top because 6 bars, and top joints are ball and socket, bottom joints are universal joint. If you don't remember, universal joint is 2 degree freedom system, ball and socket is 3 degree freedom system. And each bar can elongate and shrink without rotating. So this is called the prismatic joint, sliding joint. So bottom is fixed to the ground, so don't count this as a rigid body. You only count things that possibly can move. Probably everything moves except the bottom one. So count the number of rigid bodies. For example, this and this is two rigid body because they're moving against each other, right? This part and this part, they're moving against each other. Here, rigid body, which means there's no relative motion inside the body. Everything is moving together. I will give you 3 more minutes. This should be like 1 line of calculation. Should be able to do it quickly. Let's move it up. Oh, still dirty. How many people need more time? Oh, wow. All right, for the sake of time, you can talk to your friend and then to find out the solution. Well, I was talking anyway, just now I'm gonna be louder. Any question you can ask, any question, anything confusing in this picture? All right, let's wrap it up. Yeah, you have a question? Let's wrap it up. I heard a lot of like sound. Does that tell anything about it? How many degree of freedom you got? And of course you have a 6, right? Because you have to be able to tilt 3 degree of freedom and then moving in and out and then all 3 degree of freedom, right? You need to get 6. Let's count, right? How many rigid bodies? 1. And then there's a 2 each member, so 12. Right? So it's 13, right? 12 plus 1. So how many degree of freedom is that? 13 times 6. And how many universal joint? 6. How many ball joint? Ball and socket joint? And how many prismatic joint? Each prismatic joint, get rid of 5 degree of freedom. You can, they're all 6s. You can calculate 13 minus 2 minus 3 minus 6. Ball joint have 6. Prismatic has 6. Universal joint has 4. There we go. Yeah, it allows to move 2 degree freedom, not 4. So 13 minus 4 minus 3 minus 5 is 6, right? Just 1. 5, 4, 9, 12. So 13 minus 12 is 1, times 6 is 6. Get it? All right, let's move on to a real highlight of today's lecture. So virtual work is a seesaw. Let's start with a seesaw. It's very easy. This easy concept can be confusing later, so stay put. So can you pass your keys to the corner where the passage is? Like if you're in the middle, send it toss to the right or left. And then if you are sitting there, just tossing to the middle so that everybody is quiz note is in that along the line, and then TA come out and collect them. Yeah, pass to the corner so people right next to the passage will be able to collect all of them. All right, let's talk about virtual work. How many people heard about virtual work? About half. Where did you learn? 2W3? Okay, so the content's the same. Like we're talking about the same thing. I'm gonna teach you how to use in your design because virtual work is so powerful. So I draw a seesaw, very simple seesaw, right? One length is shorter than the other one. And then I'm providing input. This is where my input power come in, and this is where input power, output power coming out. So if you think about a situation where there's no energy loss and energy input from input side, which is, you can think about virtual work as a velocity or a very small movement. If you think about small movement, it becomes energy conservation. If you think about velocity, that becomes power conservation. Does it make sense? Power input and output should be same as long as there's no loss. Same for energy. If there's no energy loss, there's input energy, output energy should be same. So let's just start with the distance. Imagine you have a very small movement. In this case, it can be a little large. I guess once you become large, you have a cosine sine issue. So let's make it very small. If you apply F1 on delta 1, and what is the energy input I give to the system? I'm applying force F1, and it moves very small, but delta 1. What is the energy I give? What is energy? Energy is what? Force times distance, right? So energy input, force times distance is, in this case, delta 1. And if there's no energy loss, ball bearing is really good. And there's no air drag and whatsoever. And output energy is what? F2 times delta 2, right? What I want to know is if I choose a motor or some actuator means some sort of system that can generate power, generate movement. So motor is actuator, engine is actuator. This is terms we use in robotics and academic world to try to generalize some sort of force source. And I want to know how much force I'm going to get. You can draw a free body diagram. Let's do the free body diagram first. This is L1, L2, and then you want to measure how much force I'm resisting. And you can just do the moment balance here about O and equal. You can take a positive part, F1 times L1 plus minus F2 times L2. Should be 0, right? Because you have to balance the moment. This is a positive moment. This is a negative moment. So that's become negative. So if I want to know F2, which is F1, L1 divided by L2. This should be L1. F1 times L1 divided by 2. This is how you get it, right? If you use a free body diagram, right? And if you use virtual work, only thing you need to do is calculating the motion ratio. What do you mean by motion ratio? Movement ratio. So when input delta 1 is moving certain amount, compared to that, how much the output is moving, right? So in this case, it's a symmetry, right? If you have a seesaw, if this length to this length is 1 to 2, which means this delta to delta 2 is 1 to 2 as well, correct? I'm gonna go back to that later, but in this case, isn't it obvious? Or not obvious? I will explain a little bit later. So if I repeat that, delta 1, delta 2 ratio is same as L1, L2 ratio. So now you can calculate delta 2 times L1 is equal to delta 1 to delta 2. So I know delta 1 over delta 2 is L1, L2, right? Right? It's a very simple geometry. It can be complex if I move on to next one, even though it's very simple. So if we plug this in here, I want to know what F2 is, whereas the energy input and energy output is the same, right? So what we know is bring this up as well. I'm going to repeat that part. Energy input F1 times delta 1 equal F2 times delta 2. This is energy input, then energy output. So I want to know F2. So F2 is what? F1 times delta 1 divided by delta 2. Now I know ratio of our delta 1, delta 2, right? From here. So I'm going to just plug in the ratio here. So in this case, delta 1 to delta 2 ratio is what? 0.5, right? In this case. So if you know the ratio, this is going to be same as L1 times L2. So if you know the length ratio, you will be able to calculate F2. And if this is a 1 to 2 ratio, you're going to have the force. So if I summarize what I just said, if I move a little bit, and then if output is moving more, which means your force is reduced. Why? Because energy has to be conserved. Same for the power. If I'm moving a velocity v, and then output is 2v, for example, in this case is increased, right? Velocity increased, which means your force should be reduced to match the power input to power output. If you calculate energy, which is small movement in the delta, and your input energy and output energy should be same. So you can just, only thing you need to figure out is when I'm moving a delta and input and how much output is moving. Does it make sense? So I can give you a random machine, a black box machine, and you're wiggling input. And then when I'm moving like 1 meter, and the output moves about 10 centimeter. and then am I applying about 1 Newton, what is the output force will be? Should be 10 Newton, right? Because my movement shrunk in 10 to 1 ratio, which means my force should be amplified 10 to 1. Does it make sense? I can give you an example in the gear situation. You might just memorize if you use a 2-to-1 gear reduction, you increase speed, reduce speed by half and increase torque by 2, right? Imagine you have a pinion gear and then next gear, and then your shaft output is this output, and this is the input, for example. And then it's torque 1 and then torque 2. You can draw free body diagram, right? If this is a torque input, and you can calculate how much force you're applying. So if I free body diagram of the first one, I'm gonna just play with the scalar only, so you ignore the direction. So in order to meet this, in order to compensate this, you need to have a force, reaction force coming out. So if this force equal torque divided by R1, right? If this is R1, that's the force. If you plug in this free body diagram, and then your reaction force is torque output is this direction. This is F, same F. But the R is different, right? R2. So torque output will be F times R. So F times R2, which is original torque divided by R1 times R2. So torque ratio basically become gear ratio, which is the momentum ratio. Simple, right? But you can do the same thing if you think about it. If I rotate, let's say the momentum ratio is 1 to 2. If I rotate 90 degrees, how much this guy rotate? In terms of angle, right? Because in the shaft power output, the angle matter, right? If this guy rotate twice, how many rotation this guy will have? Once. So I reduce the movement, how many times? Half, right? I reduce the movement in half, which means my torque goes twice. Because your power has to be conserved. In this case, it doesn't need to be small movement, right? Because your momentum is constant. So no matter how much you move, your ratio doesn't change. When it comes to four-bar linkage and other mechanism, those number actually is constantly moving as well. So that's why we're talking about virtual work and very small movement, and then instantaneous velocity. Does it make sense? Any questions? As long as you know the movement ratio of the beginning in the input to the output, you can calculate ratio between input to output. Either it's a rotation to linear or linear motion to the rotation. As long as the ratio is given, if you figure out, you can solve this problem by just doing it. That's the concept of virtual work, which is a kind of dual to free body diagram. Free body diagram, we only calculate based on force balance. Here, we only calculate based on movement. But if you think about it, even free body diagram is based on geometry. Why we get this ratio? Because we did the force moment balance, and the moment balance has to be done through the geometry. Because this guy have a longer momentum, so I don't need to apply same amount of force to match this balance. So we're talking about same thing and projected into different perspective and then solve differently. And then the reason why I'm telling you this method, even though you can solve exactly the same thing with free body diagram, because you can do it without even using a paper. What does that mean? If you look at the machine, you can just imagine how it's going to move. You cannot really imagine how much force is going to apply unless you put it down. But if it's geometry, as long as you know that, well, this guy moves a lot more than this guy, so I know that if I push here, I'm going to be easier to push, and this here is harder to push because this guy moves less than this guy. You can think about that every single instantaneous configuration, any machine, and then think about it. Why do we need to do that? Like, I would rather get the accurate solution. You're going to design machine, right? So when you see something, you will know which linkage has to be longer or shorter. You cannot calculate every single thing unless you have optimization tools and numerical method. When you design in the beginning, almost no basis. So you can actually start thinking about this without even having any detailed design. That's why virtual work is really powerful. You can do it really quickly. So let's talk about monkey. Not really. I'm talking about rigid body motion. Before it was a seesaw, very easy, right? When this guy's rotating about this point, and then the movement ratio is basically just length ratio, which is true for any rigid body, and even 60. If you imagine this monkey is a rigid body, rotating about this point, because it's hanging on the branch using tail, right? And there's a vector, it's pointing its eye, and there's another vector pointing, and when things are moving this way, when the velocity is positive, this eye will move at the moment in this direction, which is perpendicular to that vector, correct? To some people, this is very weird or not obvious, but every rigid body, this is true, even in 3D. If this box is moving around this point, and any angular velocity, if I pick a rigid body, if I draw a vector from that point to the center rotation, and the velocity should be perpendicular to that vector, right? So same thing for banana. If I draw a vector from that center rotation to the banana, the velocity of the banana should be perpendicular to that vector. And now I'm going to ask, what is the ratio of the V1, the velocity 1, the velocity 2? Only magnitude. In virtual world, we're going to only use the magnitude, not using vector. What is that ratio will be? I think you know the answer. Just speak out. What is the ratio? R1 to R2, magnitude, right? This is rigid body, everything moving in unison, everything is moving together. You're far away from the center of mass, you're faster. It's just linearly proportional. And the reason why I'm explaining such an obvious thing, so some people can imagine, some people cannot imagine. So that can actually give you a lot of confusion later. So I hope you really get this right now. It's so obvious. But I guarantee you, so for some of you, it will hunt you down later. Like, what? This is obvious, right? If it's any rigid body, if you have any point in your center rotation, and at any point in rigid body, the velocity will be perpendicular to the vector, the pointing that position from the center rotation, and then the magnitude of the velocity will be proportional to the momentum, because if you go back to if you remember, vector calculation, V is omega cross R when everything is a vector. So magnitude matters, right? Omega is common, and R get twice, your V get twice. Do you remember this equation? It's very easy. We can do a vector here, but it gets a little complex. So we're not gonna do vector in virtual work today, okay? So let's do some practice. I have kind of weird looking 4-bar mechanism, 4-bar linkage mechanism. How many degree freedom is this one? 1. We already did, right? You can easily calculate 3 times 3, 9 minus 4 joints, so 9 minus 8 is 1. Now I want to know, when this guy is, I'm applying torque 1, I want to know what torque output. This is not super simple, right? This seems complex, right? But if I use the concept of virtual work, you know that this point is moving perpendicular to that vector, right? This vector, and moving this way. And that point is moving perpendicular to that vector, because this is the center rotation of this rigid body, right? So what I want you to do is I want you to identify all the rigid bodies in the system, and I want you to find out all the center rotation of the rigid bodies. And then I want you to figure out the ratio of those movements. So now the middle linkage has a 2 joint. None of them are underground, so I don't know where the center rotation of this guy is. But we know this point is shared by this linkage. This point is shared by this linkage. So if you think about the middle link, this point is moving this direction, and this point is moving this direction. Which means this rigid body at this moment is rotating about that point. Instantaneously, only. Can you imagine? If you don't believe it, I'll show you. By the way, you can do this quick exercise using your SolidWorks very easily. So feel free to grab a sketch mode of the SolidWorks and draw a line, define the length, and then play with it so you can actually visualize what you're building. Even constraint, you can actually create a constraint like attractions or gears to create your machine in 2D. This takes some time, so I'm going to go back to slide a little bit. So imagine the monkey is rotating, but you don't know the center rotation. And you know that this point is moving this way, and this point is moving this direction. And then you will easily find out where is the center rotation, correct? Either you know the center rotation and then you know your interest point, you can calculate those vectors, but if you don't know the center rotation, but if you know one point velocity and another point velocity, then you draw a perpendicular line and then the mating point should be center location. We're talking about sufficient necessary condition, right? So we can do the inverse thing here. That's called instantaneous center rotation. Why we call it instantaneous? Because that is true in only this configuration. Once this linkage start moving, that instantaneous center rotation is moving as well. I can give you another example. If I have a circle, like a wheel running on the ground, and then it's spinning like this. And can you find the instantaneous center rotation? It should be contact point. This is the most like unintuitive thing. If you think about any point in this line, we know that this is moving forward. And then if you think about any point here, at that moment, this guy is moving this direction. So instantaneously, at this moment, if you pick a point, I know exactly what direction and how fast it's moving. Because in this particular rolling case, that's going to be the instantaneous center rotation. It's not very obvious. This is more obvious, right? We know 2 points of velocity of 2 points, and instantaneous center rotation, because this is a rigid body, has to be where the 2 vector line that is perpendicular to the velocity meet, right? So, Steve Jobs, the Mac is not as good as before. I think the best time of the Mac was 2011. All right, so I'm gonna edit the sketch. So this is one thing you can do. You can define length, and you can create this kind of 4-bar linkage whenever you want to really think about how to design mechanism. That's not cool. So I need to get rid of this. Now show it. Awesome. So this is a 4-bar linkage, 1 degree of freedom, right? 1 angle will define the configuration. And you can change very easily in SolidWorks. I want it to be 160, for example. Boom. And the behavior change, right? I'm going to make this guy longer, 45. Boom. Make this guy a little shorter. 120, 130. So, make this guy a little bit shorter to make space a little more convenient. So let me repeat the thing. This point is moving this direction. This point is moving this direction. So if I elongate this line, no, there's some cool trick. It's done automatically. Sometimes it makes you really difficult to manage. So I'm going to elongate this line and then make this collinear. And I'm going to do the same thing and make this two collinear. And when I move these linkages, you see that mating point is moving around? I can actually make it perfectly go away. Come on. So, SolidWorks is not cooperating today, so I will just explain here. At this moment, in this configuration, this rigid body is rotating, instantaneously rotating about that mating point, because the rule of rigid body rotation, the one that I explained, I'm going to just trim and then trim, and that point will stay. Now you can see this guy. You see that? It creates some sort of weird trajectory. So I want to prove you that's actually real center rotation in this configuration. So if I draw a line very close to this circle, not quite meeting, so I want to just point it out. And I'm going to make this guy rigidly attached to that link by making a length fixed and angle fixed. That's too complex. I'm going to just make it block. Click this and click this, shift, and you can make it block. Block. Okay, you need to always click OK. So now the middle link has a little arm. You see that point in the middle is not meeting those instantaneous center rotation, but when around this point, that point is not nearly moving. Instantaneously, that piece, now that piece, the middle piece is not rotating about that joint anymore, right? But near when this configuration, that rigid body is rotating about that joint. Do you see that? I can zoom up a little more to see things better. So when I'm rotating this, so instantaneously that middle link is rotating about that point in this configuration. When I'm moving away, it's no longer true. No longer true. But around this point, that's instantaneously rotating. In that moment, that's exactly rotating about this point. Why do I talk about this? Because if you find out instantaneous rotation point of each rigid body, which means everything is rotating, purely rotating. Which means if you know the point, interesting point, if you know the vector length, you know the velocity ratio right away because it's rigid body rotation. Remember the monkey, right? Then you can solve every linkage problem. So this is procedure written down, and well, this is probably better precision. Identify input output port. Usually you have an input is an actuator, output is task, like a hand or a gripper. And check with the energy storing and dissipating component. You probably don't have it, but sometimes some people have like springs or some sort of energy dissipating mechanism. Friction is one of them. Otherwise, energy conversion doesn't work. Energy input output is no longer the same, or virtual work doesn't work. assume there's most of the system it doesn't have it, and then identify all the rigid bodies. In 4-bar Linksys case, there's 3 rigid bodies, and then we identify 3 center rotations. And then now you know all the instantaneous center rotation. Now you can discover the velocity ratio of any intermediate point. And eventually you can be able to calculate the input to output delta ratio or input velocity to output velocity, and apply virtual work to calculate ratio between input, output, force, or torque ratio. Get it? One simple example. This is actually almost identical to scissor lift. You guys remember scissor lift? This is exactly the same as scissor lift. I'll use this side. I'm going to make drawing a little simpler by making this ratio 1, this ratio 2. And this guy is sliding against the surface, just sliding against the surface. I'm pushing with some sort of force, and I want to know what this force output is. So what's the procedure? Identify rigid bodies, right? Here it's very simple, one rigid body. Now, where is the center of rotation of this guy? I wish I have some linkage that is anchored to the ground so I can start from it, right? But there's no rigid body in this case anchored to the ground. So let's find out the known velocity directions. Then you can calculate the center rotation, right? So which point you know the velocity? Which point you know the velocity? The point that touching the ground, we know that this is velocity which direction? To the left, right? Because I said it's sliding against it. So instantaneous center rotation of this rigid body should be somewhere around this line. Either ground, under the ground, on the top. Because if it's that center rotation, every part of the rigid body should be rotating 90 degrees to that vector, right? Another point we know the direction. To the left, that point is definitely moving up. So instantaneous center rotation should be perpendicular to that point, to vector, to the velocity vector. So this one doesn't meet that one doesn't meet here, but these two meet at this point. Correct? So it's hard to believe, but actually in this configuration, in this moment only, this rigid body is rotating about this point. So now what you know? Now we have one rigid body, so there's only 2 points. Point A, point B. Well, let's just keep input and output. V input and V output. What's the ratio between V in, V out? If this is ratio is 1 to 2, what is this ratio? 1 to 2. Because this rigid body is rotating about this point, and then velocity is proportional to the momentum. Right? Monkey, you can keep on reminding me monkey case. This body is rotating about this point, and this point is moving velocity 1, and that moving up velocity 2, because the ratio should be ratio of the momentum from the center rotation. Does it make sense? Now we know the velocity ratio. V output is twice of V input. And if you think about virtual work, power input should be power output, which is force 1 times V1 should be same as force 2 times V2. If you want to know force 2, which is F1 V1 versus V2, we know the V1 V2 ratio, so F2 should be half of F1. This calculation should be very easy, right? As long as you know the ratio of the force should be inverse of the ratio of the movement velocity. So this calculation, you can make a mistake, but you can check. That is longer, so that guy is moving faster than this guy, so force should be lower. You can double check. This is the power of the virtual work. You can check without even writing down anything. Of course, you can do it with the free body diagram, but you don't need to write down anything. Looking at it, if you become really good, just looking at it, and then you're virtually drawing. Okay, it's moving this direction 90 degree, moving this 90 degree. That center rotation. Oh, this length is shorter than this one, so the force will be reduced. Velocity will be faster. You can just look at the mechanism and then figure out you're going to gain the force or lose the force. Understand? That's why virtual work is very powerful, because human is really good at visualizing. Some are not, some are better, but if you get used to it, you can do things really quickly. Understand? So scissor lift is kind of same. When scissor lift is moving up, this point is always staying vertically, this guy is sliding on the ground, and the rest of the mechanism kind of similar way. So just figure out how it moves, and then you'll be pretty much done. I want to give you one example again before calculating the planetary gear. Wow, I should bring the other laptop. This is pretty slow in every way. I will show you this linkage later. Let's calculate the planetary gear ratio. In the homework, I give you a little more complex version, but the process should be exactly the same. So if I draw the planetary gear has a sun gear, and planet gear, and then ring gear. In this case, there are 4 planets, right? And I want to draw only one of them. This is ring gear, this is sun gear, and this is planet gear. And ring is fixed to the ground, and my input is sun. And my output is the carrier. Okay, carrier is that the piece that holds this planets around, and that's become output. So I want to know how to calculate the gear ratio between sun gear to the planet carrier. So again, using the virtual work, you can probably do this in a free body diagram as well. What do I need to know? First step is rigid bodies. And then second step is, where is the center rotation of those rigid bodies? Correct? So I have, this is a rigid body which is not moving. This is one rigid body. Where's center rotation? In the middle, in the center. It's really easy. Where's the center rotation of this planet gear?
Top edge.
It's top edge, because it's rolling around the ring gear. So every point at this moment, the point is moving perpendicular to that vector. So now I know this RS, I know this is RP, planet moment arm, and I'm going to calculate how fast this guy is moving, and then I'm going to divide by this arm to figure out what omega output is. So what we know, what the intermediate point, interesting point is this point. That's a V1. So I want to calculate how fast V1 is. V1 is omega S and RS. And that point is shared by planet gear, right? So I want to know how fast planet gear is rotating about this point, which should be same as omega planet times 2 times of RP. Correct? This guy is rotating about this point, and this guy rotating about this one. This is shared point, so the velocity should be same. So now I know the omega p. Now I can calculate V carrier, because this is a rigid body rotating about this point. If I know one point of velocity, I can easily calculate the other point. The length ratio is half, right? So VC is V1 divided by half. Correct? Because this is twice longer than this one. Now I want to know the omega c, which is VC times VC divided by RP plus RS. I'm talking about the angular velocity of the carrier, right? Because carrier has a rigid body that actually delivers the power, which is rotating about this point. So now I want to know relationship between omega s, which is sun gear angular rotation speed, and this is carrier angular speed, and I have all the relationship between them. From now on, it's just plug and chug. Okay? And then once you know angular velocity ratio, your torque ratio is inverse, right? If you get faster, you got stronger. If you get slower, you got weaker. Okay? Same virtual work. I wish you can use in your design. This is the last part of the whole lecture. If you have any question on your homework, please email TA or me, and then I can easily answer that.